Today we're going to be talking about limiting reagents and theoretical yield. So we'll delve into these topics, but the first one I want to talk about just the word reagents. What that is, that means pretty much the exact same, or does mean the exact same thing as reactant. It's just another way to say reactant is to say reagent. But what we're talking about with limiting reagents is we're just asking the question, which of our ingredients runs out first? Okay, because our entire reaction is limited by whatever runs out first. When something runs out, then we can't make any more products. I've used the example here of a backpacker with a huge backpack because this idea of limiting reagents reminds me of when I've gone backpacking with large youth groups. Inevitably, somebody shows up with a huge backpack, not quite this big, of course, but quite a big backpack. And you know that the entire trip is going to be limited by how far that person can hike, because obviously everybody needs to stick together, and so that would be your kind of limiting reagent when it comes to a backpacking trip. But to start off with this topic, we're first going to be looking at our classic example here of, let's pull that down here, of our sandwich. Okay, let's put down what our equation here is. We're going with a little bit simpler sandwich now instead of our complex turkey and pickle sandwich. Here we're just doing our basic cheese sandwich. So we have 2 pieces of bread, 1 piece of cheese, and that produces 1 sandwich. Okay, so that's our recipe and that's our product. So the first question that we're asking here is we're saying which of these 2 ingredients runs out first. So we can imagine a scenario where we have 20 pieces of bread and 12 pieces of cheese. Now, obviously, you can quickly figure out which one's going to run out first here, but here's the way you'll want to do it when you get into a chemical reaction, because they get a little bit more complicated. What you want to do is you want to look at each of the ingredients, and you want to say, okay, if I was able to make as many sandwiches as possible with 20 pieces of bread, assuming I had enough of all the other ingredients, how many sandwiches would I end up making? Okay, and so here's how you would do that. You just use your basic stoichiometry. You'd say 20 pieces of bread, and then our goal is how many sandwiches. So we put that over here, and then we put our nice little brackets in here. And then we use the ratios in our equation. So we have 2 pieces of bread for every 1 sandwich. And of course, the answer here would become 10 sandwiches. Okay, we do the exact same thing with the other measurement they give us for 12 cheese. So we say 12 cheese. And again, the question is, assuming that we had enough of all the other ingredients and the cheese was the only thing we're trying to determine is how many sandwiches we could make with 12 pieces of cheese. That's kind of the question that we're asking here. So we got sandwiches over here. So follow my method here. You'll see that it is helpful to you. And of course, we can produce 1 for every 1 piece of cheese. We can produce 1 sandwich. Okay, and so our answer then is going to be 12 sandwiches there. So what we do is we look at that, and we look at when we assumed each of the reactants was that we could use them to produce as many sandwiches as would be possible for that reactant. Whichever one produces the least product then becomes our limiting reagent. So in this case, our 20 pieces of bread is our limiting reagent. And what that means is it's going to run out first. Okay, and you can see that it's kind of common sense here. You can see that with 20 pieces of bread, you can produce 10 sandwiches. Once you produce 10 sandwiches, your 20 pieces of bread are all gone. Okay, whereas with cheese, we said, okay, if the cheese was our limiting reactant or reagent, we could have produced 12 sandwiches. Okay, but we know that by the time we get to 10 sandwiches, our bread's already out. So the fact that we could have produced 12 sandwiches if the cheese was our limiting reagent is irrelevant. We know that the bread's already gone at that time, and those last 2 sandwiches could never be produced. So we've determined that our limiting reagent is the bread. So the key here is that every calculation now after after we figure out our limiting reagent, every calculation should be based on that reactant. Okay, we don't use the other reactant at all. So we can actually kind of just cross out here the 12 pieces of cheese because we're really not going to use it anymore. Okay, there's one other question that could come up here when it comes to these limiting reagent problems, and that is they can ask the question, how much cheese is left over? This is not a very complex problem, but here's how you would do it, okay? Again, all of your calculations, once you figure out your limiting reactant, all of your calculations start with that reactant. Okay, so now we start with 20 pieces of bread, and our question is, how much cheese are we going to use when we use up all the 20 pieces of bread? Now it's going to be pretty obvious. Obviously, we use 1 piece of cheese for every 2 pieces of bread, but let's just do our calculation the way we do it with a chemical reaction so we're clear on how that works. Okay, so we would use 2 pieces of bread for every 1 cheese. Okay, and I should have put over here what we're calculating here. We're trying to figure out how much cheese we're going to use in making all of those sandwiches, and the answer is obviously 20 divided by 2 is 10 pieces of cheese. Okay, so we know that in using up all of the bread, we're going to use 10 pieces of cheese total. And then the last question, of course, is how much is left over. All we do is we take the 12 pieces of cheese we originally had, subtract 10 pieces of cheese that we use, and we end up with 2 pieces of cheese left over. And that is our answer to that question about how much cheese is left over. Okay, now the last question, and the last time you get to see the sandwich here, probably the last time at all, isn't that sad? Okay, the last question here is going to be around something called, we'll just put it up here, called percent yield. Now this is an extremely easy concept, but I think the reason people get confused is simply because of the definitions. The concept is actually a really easy one that I think everybody understands quite quickly. Okay, let's put our formula here. So we put, let's see, 2 pieces of bread. We're just going to put a B plus 1 piece of cheese becomes 1 sandwich. Okay, but now you've got to think of a scenario where you have 500 pieces of bread and you are tasked with making as many sandwiches as you can and 270 pieces of cheese. Okay, so you can do your calculation here. We're not going to do the full calculation, but we know that with 500 pieces of bread, we could calculate that we could make 250 sandwiches. Okay, and that's obviously the 270 cheese. So our limiting reagent, we could figure this out, we could do the whole thing, but it's obviously going to be the 500 pieces of bread. And our prediction is that in this operation, we're going to make 250 sandwiches. But as the operation goes along, you can imagine 1 piece of bread is broken, you drop a piece of cheese on the ground, you might have a lot of other things go wrong, obviously, until you burn 1 sandwich, in this case because they're nice grilled cheese sandwiches. But eventually you only make 225, try that again, 225 sandwiches. Okay, so this, the number of sandwiches that we calculate is called the theoretical yield. That's a T there. So that's the theoretical yield. When we're in the lab, we never quite make as much as our theoretical yield. We have a prediction that we're going to make 10 moles of something or 35 grams of something, but then things kind of go wrong in the lab. Maybe some of the substance gets stuck to the beaker, maybe the reaction doesn't go all the way to completion. Whatever it is, we end up with something that we call our actual yield. Again, our theoretical yield is what we calculate. Our actual yield is what actually happens in the lab. The actual yield will always be a little bit less than the theoretical yield. It's never going to be perfectly the same as the theoretical yield because things always go a little bit wrong. There's not a way to have such perfect instruments and such perfect tools that you actually get your entire calculated amount. So then you calculate something called the percent yield, and all you do is I'm sure that if you're thinking about this, you can probably figure this out without me even telling you. So we've got, let me actually write this out, actual yield divided by theoretical yield times by 100%. Okay, and in this case, that's going to come out to be, I kind of calculated in advance, that's going to come out to be 90%. So 90% would be our percent yield. Now that we've gone through our examples, let me just go through a few rules and just think about these as we go through these, about how to find the limiting reagent. We'll talk about that first. First of all, one at a time, calculate how much product each reactant would make. So, and here's the key here is number 2. It says you can select any product you want, just make sure that you use the same product for each calculation. So essentially, it's just like the cheese example. You find out how many sandwiches you can make of one, if that were your limiting reactant. Then you try the other one and say how many sandwiches you can make, and whichever one makes the least would be your limiting reagent, which is what number 3 says. And then number 4, going forward, use the limiting reagent for all calculations. So let's go through an actual example of a problem here. In this last part, we're going to go over an actual scenario that you might see. And in this case, you can see we have a combustion reaction. You can always recognize the combustion reactions because CO2 and H2O are the products, and oxygen is always one of the reactants. And you can see how this question might be asked. It says you have 64 grams of CH4. CH4 is methane. You could also call it carbon tetrahydride. And 100 grams of oxygen gas. And there are 2 questions. Actually, we should have a third question here as well. Okay, as you can see there, I typed it, how much excess reactant is left? So the first thing we have to figure out is we just have to figure out which of these 2 reactants is our limiting reagent. And then from there, we calculate how many grams of H2O were formed. And again, we base that on our limiting reagent. And then finally, we just calculate how much excess reactant is left. So let's go ahead and get started on this. So first of all, we're just going to, just like we said in the instructions before, we're going to take each of our reactants and we're going to assume, just play like they are the limiting reagent and figure out how much product we would form. Since the question we have is about, ultimately we're going to be asking about H2O, let's use H2O as the product that we calculate for. We could have chosen CO2 just as well, but it's going to save us a step by using H2O later in the problem. So first of all, we start with 64 grams of CH4, and our question is how much H2O, and it's actually going to be moles. We don't have to actually calculate grams right off. Okay, it'll save us one step just to calculate to moles, because we can compare how many moles of H2O one reactant would produce versus the other reactant and figure out where our limiting reagent is. So we take this like this, and we're going to break it up into brackets. Okay, so first of all, we have to figure out our molar mass of CH4. So I'm just going to kind of do this in my head, and if you have a question, come ask me. So carbon is 12 plus hydrogen is 1, and we've got 4 hydrogens, so we've got 16.0 grams per 1 mole of CH4. And let's keep our substance in there to make this really clear. We cancel out the grams of CH4. Then we use our mole to mole ratio, and up here we see that we have 1 mole of CH4 for every 2 moles of H2O. So 1 mole CH4 for 2 moles of H2O. And then we're going to get an answer here. It's a pretty simple calculation here. It's going to come out to be 8 moles of H2O, just because 16 into 64 is 4, times by 2 is 8 moles. Okay, so now we do the same calculation for oxygen gas. We have 100 grams of oxygen gas. And our question is going to be, how many moles of H2O do we form? Okay, so same process here, except for oxygen is 16 grams per mole, but we've got 2 of them. So O2 is going to be 32 grams per 1 mole. And then we need to do our molar ratios. In this case, it's 2 moles. Let's keep this really clear here. 2 moles of O2 for every 2 moles of H2O. And of course, 2 over 2 can cancel out to become 1. So we're essentially just dividing 100 grams by 32. I'll do that on my calculator and we'll figure out what the answer is. 3.125. Okay, and we can just keep that at 3.1. We'll get rid of these two here. So 3.1 moles of H2O. So now all we need to do is just compare these two calculations. This one came out to 3.1 moles of H2O. That one came out to 8 moles of H2O. So we know that after we've made 3.1 moles of H2O, we're going to be out of oxygen. Okay, so that tells us that oxygen is our limiting reagent. Okay, it doesn't matter that we could produce 8 moles of H2O with the methane that we have, because we know we're already out of oxygen by the time we get to 3.1 moles of H2O. So going forward, all of our calculations need to be based on the 100 grams of oxygen. Okay, so now the next question is how many grams of H2O were formed? Okay, so now, this is the reason we used H2O as our reactant to calculate with. We kind of are able to save a step because we say, okay, if we know we have to base all of these calculations now on the oxygen. And so we know that oxygen, we've already calculated this. It produces 3.1 moles of H2O. Okay, so all we need to do is take that one step further to figure out how many grams of H2O that represents. So we put on the bottom 1 mole of H2O. And on the top, we put H2O is 16 for oxygen plus 16.0 plus 1.0 times by 2 for hydrogen equals 18 grams per mole. A lot of these times you'll just kind of get to where you know some of these common substances. So 18.0 grams per 1 mole of H2O, and that's going to come out to be 55.8 grams of H2O. So that's our answer to the second one. The limiting reagent was, of course, the O2. So for the last question, it's just how much excess reactant is left. And what that means is, like we talked about earlier, how much of the other reactant is left over, the one that doesn't get fully used up. And we know in this case we're referring to the CH4 or the methane. And so we always start all of our calculations, of course, with the limiting reagent. So we've got 100 grams of O2. But our question is, how many grams of CH4 do we actually use up? We know we don't use all of it, but how many do we use up? Okay, so let's go like this. Put some brackets in here. Of course, we're going to do on the bottom here 32.0 grams of O2 for every 1 mole of O2. And then we're going to do the mole-to-mole ratio. So we've got 2 moles of O2 for every 1 mole of CH4. And then we're going to have to go to grams. And so we've got, we already figured this out up above, 1 mole of CH4 for every 16.0 grams of C. Let's put that in there, 4. Okay, that's a little sloppy. Let's do all of our cancellations, make sure we're good there. That cancels with that. This cancels with this. And this cancels with this. So we're left with grams, actually, of CH4. And we'll do a quick calculation on that. So our calculation comes out to be 25 grams of CH4. So nice that it was so even. And so, again, what we just calculated was we said, okay, by the time we use up all of our oxygen, how much CH4 or methane have we used up? The answer is 25 grams. Okay, but that's not the full question. The question is how much of the excess reactant is left. And so we've got to take this, we've got to take how much we originally had, which was 64 grams of CH4, and subtract from that 25 grams CH4, and we are going to get 39 grams of CH4 left over. So our last answer here is 39 grams of CH4. And again, that 39 grams of CH4 is just how much of that CH4 is left over after we've used all of it up, all of the oxygen up. We've used up 25 grams, so we are left over with 39 grams of CH4. The last question that we ask is, in the prior problem, if you only produced 45 grams of H2O, what would be your percent yield? So if we look at the previous problem, we predicted, or we calculated that we would produce 55.8 grams, right down here, 55.8 grams of H2O. So let's put that in here. Okay, so 55.8 grams of H2O. This would be our theoretical yield, because this is what we calculated. Okay, but we actually only produced 45 grams of H2O. So the question is, what is our percent yield? Simple problem, 45 grams. So it's the actual yield divided by the theoretical yield times by 100% equals our percent. Let's see here, percent yield. And that is going to be, I'll do a quick calculation there. That's going to come out to be 80.6%. So that's our percent yield. And that will do it. If you have any questions, come in and talk to me on this. This is something you want to just go for mastering, because I think you'll get it down quite easily once you just focus on it. And look forward to talking to you further on, and I hope you have a great day.